Hi class, Mr. Morris again. This is Unit 3.12, Photoelectric Effect Notes. A lot of this will seem like review to you. We've got a few things that are a little different from last year. To get started, we are talking about a wave equation in these notes. Electromagnetic radiation, as we learned, light, it can be considered as either a particle or a wave. It's got the wave-particle duality of light. You've probably heard of that before. If not, you'll hear of it in physics, the wave-particle duality of light. It behaves like a particle in some ways and like a wave in other ways. Now, a photon is a bundle of electromagnetic energy. It's a specific set amount of energy in almost like a packet of energy. Okay, so it's a specified amount. It's the basic unit that makes up all light. The photon is sometimes referred to as a quantum of electromagnetic energy. Those words are used somewhat interchangeably, photon and quantum. Photons have the same basic properties that help, they have some basic properties that help define what they are and how they behave. And these are some of the properties of light, properties of photons. They have zero mass. They have no electric charge. So unlike electrons, if you remember the cathode ray tube experiment that J.J. Thomson did, he put a magnet up to it and it deflected the beam, so he knew it was something different than light. That was a beam of electrons. Well, normal light doesn't do that. Light doesn't get deflected by a magnetic field. It has no electric charge. Photons are stable. They carry energy, and the amount of energy depends on the frequency, which depends also on the wavelength, and they can have interactions with other particles such as electrons. They can be absorbed by electrons, they can be released by electrons. And when in empty space, photons travel at the speed of light, which we know to be about 3 × 10⁸ meters per second. All right, so continuing on, when a photon is absorbed by an atom or molecule, the energy of the species is increased. So again, if a photon is being absorbed by a species, the energy goes up, it increases. When a photon is released by the atom or molecule, the energy of the species is decreased. So what that means is if an atom was absorbing energy in the form of a photon, then the electrons would probably jump to a higher energy level. That's one example of how energy would be increased. Another example of how energy could be decreased would be the electron falling back to the ground state, and at that point a photon would be released, as we read right here. Okay, the change of the energy of the species is equal to the energy of the photon released. Electromagnetic radiation calculations can be done using 2 different equations, and you've seen these equations before, but in a slightly different form in pre-AP chemistry. C equals lambda nu. Okay, so we'll look at these symbols. This is lambda, and it represents wavelength of electromagnetic radiation in meters. Okay, it looks like a V. It's the Greek letter nu, and it represents frequency of electromagnetic radiation in hertz or inverse seconds. Now, last year we used the letter F to represent frequency to make it a little bit easier because you weren't used to that. In college level classes, in AP chemistry, and in physics, you'll see it represented by the Greek letter nu. So be aware of that. And then, of course, the energy is H times frequency, which we use the letter nu. If we have a long wavelength, it's a low frequency and low energy, just like we talked about last class. Short wavelength leads to high energy and high frequency also. Note that since a photon is considered one particle of light, 1 mole of photons is going to be equal to 6.02 × 10⁻³ photon particles. The energy of 1 mole of photons is equal to 6.02 × 10⁻³ power times the energy of 1 photon. That's because, and we didn't really talk about this last year, but that is because E in this equation is actually the energy of one photon. So when I calculate the energy using h times frequency, I'm actually calculating the energy of one photon. If I wanted the energy of a mole of photons, I would multiply that number by 6.02 times 10 to the 23rd power. Note that wavelength is sometimes represented in nanometers. So because of that, this is how we'll do our conversions. To change from nanometers to meters, we just replace the nano, in for nano, with times 10 to the negative 9th. So an example would be 346 nanometers equals 346 times 10 to the negative 9th meters. If I wanted to change from meters to nanometers, I'm going to multiply by 1 over 10 to the negative 9th. An example would be 8.75 times 10 to the negative 7th meters equals 8.75 times 10 to the negative 7th meters. Cancel out the meters, put nanometers on top. 1 nanometer over 10 to the negative 9th meters. Multiply that out and you get 875 nanometers. We're going to do a little exercise here, practicing something similar to a problem from last year, but maybe a little different in a sense. The blue color in fireworks is often achieved by heating copper 1 chloride to about 1200 degrees Celsius. The compound emits blue light having a wavelength of 450 nanometers. So we've got a wavelength here. The wavelength, lambda, equals 450 nanometers. What's the frequency of blue light that with a wavelength of 450 nanometers? So our question is, what is wavelength, or what is the frequency, which is that Greek letter nu? What's the energy that is emitted at 450 nanometers by one copper 1 ion? So the energy emitted by one ion is going to be the energy of one photon. So that can be calculated with E equals h nu. We're looking for the energy of one ion. And then finally, what's the energy that's emitted at 450 nanometers? Same energy by 1 mole of copper 1 ion. So we're just going to take that energy and multiply it by Avogadro's number to find the energy for 1 mole. Here is the equation we're using for part A. We're looking for frequency when we have wavelength. So we're going to use C equals lambda times nu. This is C, the speed of light, 2.998 times 10 to the 8th meters per second. The wavelength was 450 nanometers, but because this is in meters per second, I need to convert this to meters. So we will multiply by 1 times 10 to the negative 9th to get 4.50 times 10 to the negative 7th meters. And then, of course, we're looking for frequency. Putting that in our equation, C is 2.998 times 10 to the 8th equals, and then we put our wavelength, 4.50 times 10 to the negative 7th times the frequency. So if I want to find frequency, I need to divide these numbers, divide this by that. And when you put in your graphing calculator, you're going to get 6.66 times 10 to the 14th inverse seconds, or you could say hertz. Either of those units are interchangeable. That's how we find the frequency. What's the energy that's emitted? Well, now that we've found the frequency, we can use that to find the energy. The energy for one ion equals h times nu. And we've got our frequency now. Nu is 6.66 times 10 to the 14th. So E equals h nu. I'm just going to plug it in. This number times that number. 6.626 times 10 to the negative 34th times 6.66 times 10 to the 14th. You end up with 4.41 times 10 to the negative 19th joules. That's the number of, that's the amount of energy for one ion. For one photon, which comes from one ion of copper 1, or for 1 copper 1 ion. If I wanted to know how much would be produced if I had 1 mole of copper 1 ions, I'm going to take that number and multiply it by Avogadro's number. So the energy for 1 ion is 4.41 times 10 to the negative 19th joules. The energy for 1 mole is going to be 6.02 times 10 to the 23rd power, the number of ions in a mole, times 4.41 times 10 to the negative 9th joules per mole. Also, after we've calculated that, which ends up being 265,000 joules per mole, we know that 1 kilojoule equals 1,000 joules. If I wanted to turn this into a more easy to work with number, which we often use kilojoules per mole instead of joules per mole, I would just divide by 1,000. So I get 265 kilojoules per mole. All right, exercise 2 says the bond energy of a Cl-Cl bond is 239 kilojoules per mole, and a student is determining the electromagnetic radiation needed to break 1 mole of chlorine-chlorine bonds. There are 3 parts to this, part A, B, and C. You've got it on your paper. If you want to pause the video and try it on your own, go ahead. Calculate the minimum amount of energy needed to break 1 Cl-Cl bond. Well, this energy up here is the amount of energy to break a mole of bonds. That's 239 kilojoules per mole. What if I wanted to just break 1 of those? Well, a mole is 6.02 times 10 to the 23rd power bonds being broken. So I would divide by that number, divide by 6.02 times 10 to the 23rd power to find how many kilojoules of energy is used to break 1 bond. Also, we're going to use the fact that 1 kilojoule equals 1,000 joules. 1 mole equals 6.02 times 10 to the 23rd power. Use those 2 facts to find out how many joules of energy were used. The energy to break 1 mole of bonds is this. We just said 239 kilojoules, which is 239,000 joules. And that's the amount of energy to break a mole of chlorine bonds, which is 6.02 times 10 to the 23rd power. So the energy to break 1 bond is going to be 239,000 joules per mole divided by the number of particles in a mole, 6.02 times 10 to the 23rd power particles per mole. And you end up with 3.97 times 10 to the negative 19th joules. That's the amount of energy to break 1 chlorine bond. Now we want to calculate the minimum frequency, which is represented by the Greek letter nu, of electromagnetic radiation required to break a chlorine-chlorine bond. To do that, we're going to use E equals h nu. And this time we're solving for nu. We're solving for frequency. So I'm going to plug in my energy and h, and I'm going to solve for the frequency. 3.97 times 10 to the negative 19th equals 6.626 times 10 to the negative 34th times nu. To solve for nu, we will divide. And the answer you come out with is 5.99 times 10 to the 14th inverse seconds, or you could say hertz. Now it asks to calculate the maximum wavelength in nanometers of the electromagnetic radiation that is able to break a Cl-Cl bond. Well, we found the minimum energy, we found the minimum frequency. The maximum wavelength is going to be the wavelength that corresponds to the frequency that we just found. We can find that by using C equals lambda nu. So the speed of light is 2.998 times 10 to the 8th meters per second. Wavelength is unknown, and the frequency we just found is 5.99 times 10 to the 14th inverse seconds. Now let's set up our equation. C is 2.998 times 10 to the 8th, we put that on the left, equals lambda, our unknown, times 5.99 times 10 to the 14th inverse seconds. And you don't have to put the units there. I left them there by mistake. We would divide these numbers to solve for lambda. And there's your answer. There's your wavelength in meters. If I want to find the wavelength in nanometers, I will take my answer, which is given in meters, times 1 nanometer over 1 times 10 to the negative 9th meters. Cancel out your units, and you end up with 501 nanometers. All right, there's a look at how to do these types of wave equations. You've got some example problems to work through.